Hey guys, welcome to video 77. Today's going to be a pretty short one. We're just going to work through the solution to the homework problem I left at the end of the previous video. The circuit we're working with is over here. We've got an EL84 wired up as a triode. We're working with a 200 volt power supply. Our load is a 16 ohm loudspeaker, and our output transformer has a turns ratio of 18:1. Over here on the right, we've got the plate curves for the EL84, and you can see I've already plotted the bias line, the AC load line, and I've listed the maximum signal swing limits for the plate of the tube as well. These are the parameters for the EL84. Mu is 19, transconductance 11.3 millimos, and dynamic plate resistance 1.7 k ohms. You can get these from the data sheet. It's a little bit of work. It's kind of cryptic and you have to dig a little bit, or if you wanted to, you could get them right off of the plate curves. If you're interested in a review of that, go back to video 68 where I discuss how to do that. And let's go on over to the next page and take a look at the calculations. Okay, here are all the values pretty much in the order I calculated them in. Starting up here, R prime L, the reflected load resistance, is 5.2 k ohms. R prime P is the small signal plate resistance, 1.3 k ohms. And A prime V is the voltage gain at the plate with respect to the control grid. That's 14.7. The actual voltage gain is stepped down by a factor of 18, so it works out to be 0.82. So just like the previous amplifier we analyzed, it's less than 1. That happens fairly often with this type of amplifier. IP sat is about 78 milliamps. VPK cutoff is 408 volts. VPK minimum is 118 volts, and remember, VPK minimum is where our AC load line intersects the VGK equals 0 volt curve, and that's right here at 118 volts in this example. All right, V prime O maximum, that's the maximum positive signal swing we can get at the plate of the tube. It's equal to 208 volts in this case. The actual maximum signal swing we can get at the output is stepped down by a factor of 18 by our output transformer, so it's stepped down to about 11.6 volts. And this may be actually a negative voltage. It depends how we connect the secondary of the transformer. We don't have phasing dots shown, so we don't know whether the phase is inverted or not, but we'll assume it's not. So we get 11.6 volts out for this 208 volt swing. V prime O minimum, that's our maximum delta VP in the negative direction. That's negative 82 volts, step down to negative 4.6 at the output. Now notice we've got a pretty big asymmetry in our positive and negative output swing. That's not a good thing. If we want to get the maximum power out of this amplifier, we'd like these to be equal in magnitude. They're not, so this is not really a good design. I wouldn't build this one. But these are the values we come up with. It's very asymmetric on its clipping points. That's pretty undesirable. Moving on to our maximum power output, this is going to be our maximum unclipped output power, which works out in this case to be VO min squared divided by RL. We use the lesser of VO max's magnitude and VO min's magnitude, and we get 1.3 watts peak. If we're dealing with a sine wave, the RMS power is the max power divided by 2, so that's 0.65 watts RMS at the output before clipping occurs. And that's not very much considering how expensive this is going to be. And again, I wouldn't recommend this as a practical output stage for an amplifier. And finally, coming over to these green boxes, I thought I'd throw some new stuff in here. Our heater power dissipation, P sub H, is just the heater voltage times the heater current. So it operates from 6.3 volts, and draws 760 milliamps. We get this from the data sheet. So our heater is dissipating 4.8 watts. The efficiency of the amplifier is equal to the maximum unclipped output power RMS divided by PDQ plus the heater power. So we've got a maximum output of 0.65 watts RMS. Our quiescent power dissipation is 8 watts, and we've got 4.8 watts of heater dissipation, so that gives us an efficiency of 5%. Not very good. So again, I wouldn't recommend this as a practical amplifier. It's just an academic exercise. Now, the next video we're going to use the EL84 in the pentode mode, and we're going to come up with a much better design, and we're actually going to go through a design rather than analysis. So that's something to look forward to in the next video, and I'll see you guys then.